Hello and welcome to day 11 of Advent of Code. Again, we are going to try to solve both puzzles using Kotlin. And yeah, let's start. You enter a large cavern full of rare bioluminescent Dumbo Octopuses. Okay. Oh wow. Use the picture-in-picture feature. Maybe overlay this. They seem to not like the Christmas lights on your submarine, so you turn them off for now. There are 100 octopuses arranged neatly in a 10 by 10 grid. Each octopus slowly gains energy over time and flashes brightly for a moment when its energy is full. Although your lights are off, maybe you could navigate through the cave without disturbing the octopuses. You could predict when the flashes of light will happen. Okay, let me actually close this because it's getting a bit annoying. Each octopus has an energy level. Your submarine can remotely measure the energy of each octopus, your puzzle input. For example, this. The energy level of each octopus is a value between 0 and 9. Here, the top left octopus has an energy level of 5, the bottom right one has an energy level of 6, and so on. You can model the energy levels and flashes of light in steps. During a single step, the following occurs. First, the energy level of each octopus increases by 1. Then, any octopus with an energy level greater than 9 flashes. This increases the energy level of all adjacent octopuses by 1, including octopuses that are diagonally adjacent. This causes an octopus to have an energy level greater than 9. It also flashes. This process continues as long as the new octopuses keep having their energy level increase beyond 9. An octopus can only flash at most once per step. Finally, any octopus that flashed during this step has its energy level set to 0. As it used all of its energy to flash. Adjacent flashes can cause an octopus to flash on a step, even if it begins that step with very little energy. Consider the middle octopus with a 1 energy in this situation. Okay, after step 1, every one is 1 higher than the one in it is also flashing after step 2. Okay, an octopus is highlighted when it flashed during the given step. Here's a larger example above progress. 20 steps. A step. Okay. This is a great input to some tests today. Okay, after step 10, there have been a total of 204 flashes. Fast forwarding, here's the same configuration every 10 steps. Okay, 20, 30, 40, 50, and so on. After 100 steps, there have been a total of 1,656 flashes. Given the starting level of the Dumbo octopuses in your cavern, simulate 100 steps. How many flashes are there after 100 steps? Oh wow, the input is much smaller than I expected, to be honest. Let's go to IntelliJ. Alright, let's move in the code, the puzzle input, move it to the root again, and let's name it day 11. All right, so let's create a package for day 11. So yesterday we had a problem and this took a while to debug, and I said, hey, if we would have written tests for all the small pieces of code, that would have been easier. So let's actually try to do this today. And I guess we can do this by writing some tests, and I will copy this here this example because we can use this to verify that we get the same results. So I will create a file for this too, day 11 test, and we load this file. Oh, no Java, we want Kotlin, day 11. Okay, so how do we want the data to look like? Read octopuses. And I guess we will again use a list of lists and then maybe create an octopus class for that. And again, the X and the Y are telling us the position in this grid, because I think we still want to, there's no different way to structure the data here. We can use this grid because the position is actually important as well here, because we need to find the neighbors again. And it's a small grid, so I see no problem with that. Now, data class, there are two things. Every one has energy level. Let's call it energy. And there's one interesting piece here. Yeah, an octopus can only flash at most once per step. This means during a step we might need to remember whether it flashed already. The energy can be an int. And let's pass in the file name. And then let's say to do. Because this time we will write a test for those things to make sure we actually load the things in a way. Expect them to load. Awesome. And then let's see. Test reading. Octopuses equals read, and our file name in this test is day 11 test txt. And now we need to assert that they equal, oh, sorry. No, not from Kotlin test. Oh, we already import the unit, and then we say, we expect something, and this will be a list of list-offs. For this example, we will just create those manually, I guess. Oh, that will be a lot of work though. Let's maybe make it differently. Let's say we only check a couple of interesting ones. Let's say octopus 0, 0. That should have an energy level of 5. And let's check some other interesting ones. The last one maybe, that is index 9 and position also 9. So let's say 9, 9 should be 6. And then let's use a random one. Index 4, 0, 1, 2, 3, 4. 4 should be 3. That is not perfect. but if this is fine and read octopuses is not complex, then I will be happy with that for now. Okay, syntax error. So this should now fail. It's expected. File name is never used. Okay. And yeah, it fails. Okay, so the file name, we read lines, and then every line we map to line line. Now we can look at the characters and map those to an octopus. Let's maybe get this octopus of value to int. And what's the problem here? Quiet int found octopus. What does this mean, require int? Oh, this is to char array maybe. Oh, and then it's to int, digit to int, yeah. Okay, and now we return this. And yeah, we always use diagonal where it doesn't really matter which position we are looking at, so maybe we should also look at something like this. So it's 0 and 9. 0 and 9 should be energy of 3. And if you reverse this, 9, 0 should get 5. So let's run the test. Oh, awesome, and it is failing. Now we need to figure out, is it our test? Three, 0, 1, 2, 3, 0, 1, 2, 3. Yeah, that should be 1. What kind of mistake did we do here? Okay, so apparently we can read stuff. That is great, but that's not actually what we want to do. Let's also create our functions for later. Fun part 2 and part 1, and main will later execute 1. So now we need a way to simulate. And this means we have a list of octopuses. And we have a simulate method on it. Oh, I have a typo here. That's why it's complaining. Okay. So this is to do. How do we simulate? Essentially, we go through over every octopus and increase by 1. That is step 1. Let's start with that. Let's create a helper that we can test. Increase. And this is essentially just walking over all the elements. So we could for each, this is a row, and then for every item in a row, which is an octopus, we say octopus energy plus plus. And I think we need also a way to print those in this form, so that will help us to debug, and this will also help us in tests. Dump, maybe a dump, which will just be a string, and it will look like this too. And need a string builder. Wrap this in build string. Oh, now we have a problem with the for each. Values equals this. A little bit weird. Or octopuses. And then append octopus energy. And for after every row, we say append does this only append a new line? Yeah, awesome. And then does this return the string? I think it does. So this, okay. The great thing is we can now use this for testing our octopuses again. Test reading octopuses dump. And we do the same, we read the test file. And then maybe we print it, because no, we don't. Let's just compare. So we compare it with something I still need to write. And call dump. And the result we want to get is essentially exactly this thing again. See if this works. We only run one of those. We want to run both. Oh, we forgot the annotation. Now let's run it. Okay, it's not doing what we want. Why is that? Okay, our expected one has stuff at the end. That's not what we want. This should be this here. Let's move this here. We don't want this white space. Still a problem. This is as a new line. Oh, I see. Oof. Maybe trim this again. No. What am I missing? Oh, the trim will cut it away again, of course. I guess our dump should not need to append a new line in the last row, but this is, well, how about we just trim the string we return? Awesome. Because the nice thing is we can now use this to test our new function. We created increase. So let's test this. Test. And I guess we would want to have a smaller test case though, because this will be a lot of stuff to write again. Let's try something else. We have read octopuses. Read octopuses works on a file. Let's turn this into something that can do this from a string. Because that will allow us to create test cases without a file. And this means we want to read text here and then dump this into the other one, read octopuses from string. And here, take the input, we take the lines, and then we do what we did before, map them to list of octopuses, return. Awesome. Now we can test our increase. Let's create read from string and dump. Let's say we have a string that looks like this: 5432 1111 0882 0144. And now we say octopuses equals read from string input, and then we dump them again and expect them to look exactly the same as before. See if this works. It does. Okay, now we can easily test increase, which is essentially the same test we call increase, and then we dump them again. But now we want them to actually have increased, so it's 6, 5, 4, 3. Those are our 2s. 1, 9, 9, 3. 1, 2, 5, 5. Test. Awesome. Okay, we simulate, which means step 1, we increase. Now we need to perform flashes. Okay, then any octopus with an energy level greater than 9 flashes. This increases the energy level of all adjacent octopuses by 1, including octopuses that are diagonally adjacent. Sure. Let's see, how do we do this? We can now find all the ones that need to flash, then find all their neighbors. And then with those, do it again. Okay, let's imagine the following. We have a flash function. This will find octopuses to flash. Create list of neighbors. Then do we return it? Do we increase them? What do we do with the neighbors? So it's essentially a loop, and I'm wondering what the end condition should be, or who ends the thing. I guess we would create a list of neighbors. Then after we have done all this, we run through the list of neighbors, increase all of them. Then we flash them again, return neighbors until the list of neighbors is empty, I guess. So maybe just return the list of neighbors, and the list is probably again a position. And maybe is there a position or something like this? And swing and reflect? No. Maybe this time we actually create a position, because the pair last time was really confusing to use. So position is something with an X and a Y. So we return a list of neighbors. And then we do the following. We take this, we flash, we have a list of labels. Then we, while neighbors is not empty, we go through this list, increase the neighbors, so we need something. Another increase function, but this one gets a list of positions. And then we save. As long as we have neighbors, we increase all of them. And there can be duplicates, which is fine. And then we say, okay, let's flash again. And if there's still neighbors, we continue. And we do this until we do not have any neighbors coming out of a flash. So no one flashed. Let's see. So to find the octopuses to flash, we need to loop over them for each indexed, which is actually only need to go over the indexes x, and then we go get x, take the indices of that, which is y. No, sorry, it's first y and then x. Or if you do this wrong, that will be a problem. And then you have an x and a y, and see if x is oh yeah, now we need to check for flash. Is this a function on the octopus? Can flash, maybe, if so we need energy, was this larger? Greater than 9. Needs to be greater than 9. It cannot be 9. Okay. And if it hasn't flashed this step, and then it can flash, which means flash will be true, energy will be 0. Now, if let's get the octopus first. The octopus is get y, get x. Yeah, okay, let's make this an array axis. And then if the octopus can flash, then we will flash it. And we need to remember its neighbors. Add all. And now we need to get the neighbors. We need a function for that too, and we can write a nice test for this. Neighbors of x and y. Returns a list of positions. Still a to do. Neighbors of x and y. Okay, I guess this is the algorithm. Now we need to fill out the functions and test them. So let's start with neighbors of, and let's move this one up so that this is a nice list. Which one should we start with? Neighbors of or let's start with the neighbors. And we have written a similar function before. Okay, let's start with the top row, which means 3 positions for the top. This is x minus 1 and y minus 1, and then it's x plus 1 and minus 1. So this is the row above. That's why it's y minus 1. Then in the middle there are only 2 because you only need the one before and after, because the one in the middle is our point. And then we need the 3 below, which is plus 1 on y and now we only need those that are actually valid. So let's filter those. candidate needs to be x needs to be equal or be smaller than equal or be larger than 0, and x needs to be smaller than from the list no, sorry, the size. Does it say? Range check. This can be replaced. Oh yeah, now I remember. This needs to be in indices and y needs to be in and I think I messed up. The x needs to be in somewhere in the first row. Doesn't matter which row, so we just pick the first one. And let's test this. Let's write a test. Test neighbors of. Let's use the same example. And then set equals. We want expect a list of. If we ask now for this list of octopuses, we want the neighbor of 0 and 0. What do we expect to get? We expect to get 0, 1, and we expect to get 0, oh no, 1, 0, and 0, 1, and 1, 0. So the 4, the 1, 1. Let's test this. Awesome. Let's test some more. Let's get the neighbors of this one. So that's 0, 1, 1, and 1, 1. We ask for 1, 1. We are expecting 3, 4, 5, 6, 7. Let's maybe try. Let's try getting the values. Or do we? No. Yeah. No. We want 0, 0, 0, 1, and 0, 2. So this. And then we want 0, 1, and 2, 1. And then we want the ones with 2, and that's probably 0, 1, and 2. And this one looks wrong. We want 0, 1, and 2. Yeah, okay, let's try this again. Okay, this seems to work. We could also try this one just to make sure we are doing everything correct. This is 0, 1, 2, 3, position 3, 3, and we expect those to be position 1, this 2, so 0, 1, 2, 2 and 3 on the x-axis and 2 on the y. Two, 2, 2, 3, and 2. No. Wait a second, 4, 2 is not a valid one. And then there's only one more position. So those are the two above. And then there's only this one left. This is on the y a 3, and here 0, 1, 2, 2, 3. Test. Works. Awesome. Can keep this method. Now we need increase. That should be nice as well. You only need to go through those positions. Neighbors for each neighbor. This is get of neighbor y, and then the x, and then we increase the energy here. Super easy. Let's try this. Increase neighbors. Turn this into a test. Let's steal this here. And now we turn this into a list of lists of octopuses. And we say increase the neighbors. And we use the function we just tested. Neighbors of, what was the last one? 3, 3. And now we dump them and see whether this has happened, what we expect. Okay, we say we want to increase the neighbors of this one. So this should be a 5, this should be a 9, and this should be a 3. Did this work? Yes, it did. Awesome. All right. Did we implement everything we need? Because then we could try to simulate, which would be awesome. Let's see, what's the example? Let's take, should we immediately take this one or the simple one? Let's take the simple one first here. Read from string, and our string is this, and then we simulate. simulate once. And we expect this to look like this. Oh, and we need to reset the flashes. That's something we have not done yet. But we can do this. So let's just run this first. Oh, that was the wrong test. Simulate once. Wow, that worked. There was one thing I was just saying. Whenever we go through this loop, after the simulation is done, we need to reset, which means we go over this list and then every octopus we call reset, and reset essentially just means we set flash to false because in the next round it should flash again. Awesome. Let's run this with the actual input.
Well, we're waiting.
Before we actually try to run this, let's try this minimal example and simulate the 2 steps, because those require at least flashing once, and then we see if this is working as we expect. Write a test for that. Test minimal example. And then we read the octopuses from a string. This is our input. We simulate once, and then we assert that the octopuses now look like this. Because there's one thing I'm wondering. We are increasing. We prevent octopuses from flashing if we if we have flashed them in one step already, but we are still increasing the energy, and I wonder if this is correct to do. Let's have some water. No. Oh. Yeah, this is definitely wrong, because we need to turn those into a string first. Oops, sorry. It's still wrong. And why is it wrong? Because the ones that flashes still increased, which is apparently wrong. Because when one of them flashes, it should not affect the other ones, apparently. Is this right? Should not increase any further. Finally, an octopus that flashed during this step has its energy level set to 0. It used all of its energy to flash. But I think we can ignore this, and just at the end we set everything to... We already have resetted. So we can do if it flashed, then we set the energy back to 0 and set it to... I didn't flash. Run this. Oh wow, now the minimal example is correct, and there was another step here. Let's throw this in. So if we simulate this again, we should get those. Dump. Should get those numbers. Let's see if this is correct. Seems like it's still correct. Awesome. We could now do, should we do those? Yeah, let's, how many steps are those? A bunch. 10 steps. Should we try those? Yeah. 10 simulations. Let's add a test. This is our initial step. And let's read those. Read from string. No, not and dump. Read octopuses from string. Pass in this string. Simulate. And we expect them to be see, yeah, with this. Let's run this. Okay, this is right. So now we can just copy this and do this a bunch of times. Let's also name those step 1, just so that we can still see where we are. Step 2. Copy, 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 copy. Let's see, and this is step 1. And step 2 should look like this. Then we have step 3, like this. This is now maybe optional. We could just simulate the actual code and see if we get the right value to solving this puzzle. But as I mentioned before, like yesterday, we did a long, kind of longish, definitely longer than I wanted to, debug session. And this time I want to find the errors while we write the code with some tests. Sorry, got to update the comment. Step 6, step 5. This is step 7. And then we have step 8. And yeah, if there is a bug, we might find it here. Step 9. And finally, step number 10. Let's see if we get the same results. Oh, we didn't. Now the question is, in which step are we? Oh, okay, this might just be stupid mistake while copying stuff. Yeah, there's a backtick here. Let's run this again. Still an error. Oh, backtick at the beginning. What the hell? Run this again. Ooh. We passed all 10 simulations, so I guess I trust this code enough now. Let's see if it's good enough to solve part 1. What do we want to do? We want to read our octopuses from day 11 txt. Let's make sure the right one, yeah. And then we can simulate those for how often? 100 steps. Repeat 100 times. Simulate. And what is the answer? Given the starting energy levels of Dumbo Octopus in your cavern, simulate 100 steps. How many total flashes are there? Okay, this is something we didn't anticipate. We need actually a count here. And then let's add the test for this too, I guess. Was there an example here? There are 204 flashes. Awesome. Let's add this here to our test, flashes. So after those 10 steps, we expect 204 flashes. Now we just need to keep track of them. How do we do this? If we flash, this is where we know how many octopuses flashed. So we need to keep track of those. Let's add a counter, I guess. And this is flashes 0. And we now return again a pair, I guess, which will be the number of flashes, an int, and the list of positions. All right. This will be now a pair of flashes and the neighbors. And whenever we flash one, we say flashes plus plus. And now here we need to go back and say this is our flashes and our neighbors. Oh, the other way around, flashes and neighbors. And then how do we do this? We need to deconstruct this into our existing neighbors and a new number. Additional flashes maybe for now, and this will be a val and new neighbors, and then we say neighbors equals new neighbors and flashes plus equals additional flashes. And then at the end we return the number of flashes. I guess instead of counting them, the reset function could actually have returned the numbers too, since it goes over all of them and resets them. Anyways, so this will give us the count, but let's see if this is already the right one. No, we only get 29. Why do we only get 29? Oh, because if we call simulate, we still need to add them up. Something we do not do here. So maybe create an extra test for that. And we say create another simulate method that will give us the numbers. A list of octopuses. Octopuses. So far I always said octopuses, right? Need to look this up. And then we give in how many times we want to do it. Essentially we call the other method simulate, but we end up counting. Flashes is 0, and then we add the flashes we already got and return it. And now we create a test flash count function. Let's run the original one just to make sure it still passes again. Okay. Now we start this. Start with the same number. We say count equals octopuses simulate 10 times. And now it should be, was this 204? Yeah. Let's run this test. Let's compare. We got 204. And something we actually didn't do is let's run all of them. Yeah, all tests are green. So let's go back to part 1. Now we can write this differently and say flashes equals octopuses simulate 10 times. And then, no, stop. We need to simulate this 100 times, right? Yeah. Oh, we can also do, yeah, let's also write a test for the 100 times just to make sure we are super correct. Test flashes count after 100 times. Oh, sorry, 100 here. And we throw in this number. That would be ugly to debug if this is now wrong. Don't expect it. Yeah, okay. So we simulate this 100 times and get what? On part 1. Let's go. 1615. And that's the right answer. Let's see what part 2 has for us. It seems like the individual flashes aren't bright enough to navigate. However, you might have a better option. The flashes seem to be synchronizing. In the example above, the first time all octopuses flash simultaneously is step 195. Ooh. Let's actually look at this. Test all flashes. All flashes example. We take this. We simulate it 195 times. And then we print this. That's the wrong test. Yeah, that's true. All of them are flashed. Nice. Let's turn this into an actual test. Run it as a test. Yeah, nice. Okay. If you can calculate the exact moment when the octopuses will all flash simultaneously, you should be able to navigate through the cavern. What is the first step during which all octopuses flash? That should be nice. We just need to have a function that can check this for us. So let's create this. We create a list of lists of octopuses. And then we need to are all flashing. Or it's all flash. No. Are all flashing. Okay, that is fine. And then we return, no, we need a boolean, so we need to check for all. All is the right one, right? Yeah, boolean. So all rows should, and of all rows, all of them should be all should have energy 0. We can't use the flashed one after the simulation step because we reset it. So we just use energy 0, I guess. Now I'm wondering, are there, like, there can be some 0 at the beginning, and they might, if they never flash, well, they will still increase. So if all of them are 0, then all of them should have flashed at that point, I think. So let's give this a try. This should be true now. Let's maybe turn this into all flashed because it just happened. Okay, and now we need a function that finds us the first simulation step where this happens. Simulate until all flashed. And then we return the steps. While not all flashed. Need a step? Well, no, we do not need a step. Well, we need a step. It's 0, and then we return it here. And then we simulate and increase the step counter. Now we can test this one. Test simulate until all flashed. We take this example again. Steps simulate until all flashed. And since we already know for this example it needs to be 195. Let's give this a try. Set the annotation. Stack Overflow error. Why is this happening? Oh, we are calling ourselves. Simulate until all flashed. We actually need to call this here. See? Yeah, that worked. Let's run all of the tests. They all pass. Then let's call part 2, which is we read the octopuses, we simulate until all flashed, and then we look at the steps. Let's run the main function. 249. Is this correct? Yes, it is. Awesome. We solved both puzzles using Kotlin again. I'm curious how you solved the problem. This time I'm really happy how we used the tests. That was really smooth. We didn't have awkward debugging sessions, so that was really nice. And yeah, depending on the next problem, we might keep this pattern, I guess. So see ya. Bye bye.